Let's talk about determinants. So here is a definition. So we only talk about determinants for square matrices. So let's say we're talking about a square matrix, and let's say it's n by n. In the simplest case, when n is 1, so A is just a 1 by 1 matrix, so it's just got one number in there, the determinant is just that number. It's just whatever number is in there. When n is bigger than 2, then things start to get complicated. So let's say that A is, so here's the entries of the matrix, and it's n by n, so it looks something like this. Then the definition I'll give you, which we're going to learn many different ways, that there are many different equivalent ways to do this, but the definition I'll give you is like so. So I'm going to write this, and by the way, when I write A with subscripts, A sub ij is just the matrix that I get by deleting the ith row and the jth column from the original matrix A. So let me explain this line. We can sort of view this as going across the top row in the following sense. I'm going to take this entry, little a sub 1, 1, and multiply it by the determinant of big A sub 1, 1, which of course is just the matrix that I get by deleting the row and the column with this little a sub 1, 1 in it. So that's my first term. And then as I go, there's going to be an alternating pattern of plus, minus, plus, minus. So this first one was a plus, and then that's going to be a minus, and so on. So the next one's a minus, and basically I keep going across this row. The next thing I'm going to do is a sub 1, 2 times the determinant of the matrix that I get by covering up the row and the column containing a sub 1, 2. And I proceed. The next one would be little a sub 1, 3 times the determinant that I get by covering up that row and that column, and so on. Of course, this is, at some point I get to the end, and I have an alternating pattern of pluses and minuses, and depending on whether n is even or odd, the last one might be a plus or a minus. So I'm expressing that this way. If n is even, then, If n, I think that this should be n minus 1, right? Because, yeah. All right. Great. So, yes. So, I get to the end, and I do a sub 1n with the appropriate sign in front times this determinant. Okay. Let's do a simple example. So I told you how to do a 1 by 1 determinant. That's really easy. Let's actually use this definition to do a 2 by 2 determinant. So I go a1, 1 times the determinant of the matrix that I get by covering this up, which is a 1 by 1 matrix. And then I go my alternating plus minus pattern, and so I keep going across. So a1, 2 times the determinant of the matrix that I get by covering this up. And I'm going slow. Of course, the determinant of a 1 by 1 matrix is just the number inside. So we get that. This is worth remembering for 2x2 matrices. You know, in practice, we're going to do a lot of examples that are just 2x2s and 3x3s. We're going to do a few examples that go up to like 4x4, but it gets pretty hard and just tedious. The bigger the matrices get, it gets really tedious really fast. So it pays to know how to deal with the small matrices. The way I view this, and the way a lot of people do it, is you just go, it's like the diagonals, like the main diagonal, and then this. So it's just like this times this minus this times this. That's what we got. By the way, you'll often see people write like absolute value looking signs around a matrix instead of this notation that I've been using. So you're probably going to see me use both from now on. Yeah. All right. So let's do a 3x3. I'll use the definition. I'll try to go a bit faster. So it's A11 times the determinant of this matrix. Minus A12 times the determinant of this matrix. Plus A13 times the determinant of this matrix. And then these are all 2x2s, and I'm just going to use the shortcut that we just figured out for 2x2s. So this determinant, I go bloop, bloop. This one, I go like that. And this one, I go like that. Oops. Yeah, so this should be this one times this one. So A21 times A32 minus this times this. Okay, and then let me actually, bear with me on this. I'm trying to illustrate something. Let me write, okay, where are my positive ones? I've got A11, A22, A33. There's another positive one I would get because this is a negative times a negative. So I'll write A12, A23, A31, and then there's another positive one, A13, A21, A32. Where are my negatives? Here's a negative. I've got A11, A23, 2, so that's this. I've got another negative from here, so minus A1, 2, A2, 1, A3, 3. And then I've got one more negative, so minus A1, 3, yeah. I don't know where I pointed, but I'm doing this. So I don't think I made a mistake yet. So I get that, which is not a very nice formula to try to remember, but there's a visual way of doing this. So let me try to sneak up here and show you the visual way. I copy my numbers down. I'm going to duplicate the first two columns. So I do this to the right. I just duplicated this. Okay, one more. Bear with me. So here's the visual way. I go down, 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 and yeah, so down, down, down. These give me my positive terms. So this times this times this. So for example, here I've got an A11, A22, A33. That's this. And then I've got a A12, A23, A31. That's this. And then this is this. And then I have my negative terms. And I get those by going up, up, up. So I would say that this is also worth knowing the shortcut for 3x3s, doing it this visual way. Unfortunately, for higher order matrices like 4x4, there doesn't really exist a nice visual way of telling you how to do 4x4s and higher. You kind of have to use the definition or some of the facts that we're about to learn about determinants. So, yeah, actually, so let's do a quick example. I don't know, let's just do this the quick way, because that was all very, and I like showing you things that are general. However, writing this nightmare of subscripts gets to be painful. So I duplicate. And all right, so 1, 1, 1 gives me 1. This gives me 0. This gives me 2. I add these up, because these are my positive terms, the ones I go down and to the right, and then I'm going to subtract my up, up, up. So this gives me 0, this gives me -1, this gives me 0. And watch me make a mistake here. So this is 3 plus 1. All right, I think I got it. Okay. So, yeah, let me pause just for a second and tell you why are we talking about determinants. So this is the main fact that we're going to use determinants for differential equations. We are eventually going to use this linear algebra stuff for differential equations. It's been a little bit of a detour that we've been taking, but we're going to get back to differential equations. We're going to use this. The basic fact that we're going to use about determinants for that purpose is that a square matrix is non-singular if and only if its determinant is not zero. And remember, non-singular, it means the same thing as having an inverse. And so for the 2 by 2 case of that, this is basically a fact that we've already learned if you think about it. So this is a fact that I stated in the last video about matrix inverses. I told you that a 2 by 2 matrix ABCD has an inverse if and only if this number is not zero. And we didn't use the word determinant at the time, but this is the determinant. Remember, the way you find a 2 by 2 determinant is you go bloop, bloop. So it's AD minus BC. So in other words, that this is just the 2 by 2 case of the fact that I just stated, but this fact is true in general. And in the 2 by 2 case, I actually gave you a formula for the inverse, and I'm not going to go into detail here, but when you're doing n by n and n is larger than 2, there's also a formula for the inverse in terms of determinants. And it gets kind of complicated, and it's not really that practical to calculate a matrix inverse using this formula, because you have to do a lot of determinants, and each determinant is a fair bit of work. So that's why I don't really go through the details, but it's sort of a cool fact that you can, when a matrix has an inverse, you can tell whether it has an inverse only looking at the determinant, and you can tell what the inverse is in terms of determinants. Okay. So where we're going to go next is trying to find sort of smarter ways of finding determinants, and we're about to do a 4 by 4, and well, when I say a smarter way, let me maybe describe first a not so smart way. The not so smart way is using the definition. I mean, when I say it's not smart, it would work, but it would be labor intensive. I would go across the top row, so I would do 1 times this 3 by 3 determinant, and then a 1 times this 3 by 3 determinant, and then this times this 3 by 3 determinant. So, and then, right, of course, the last one. So I would have 4 3 by 3 determinants to do. And each 3 by 3 determinant is, I mean, it doesn't take forever to do, but it's it gets kind of labor intensive. So let's try to find something smarter. So here's the fact that I'm about to illustrate. The definition that I gave you, I would describe as expanding it along the first row, because we sort of go along the first row and do this number times this determinant and so on. You can actually expand by any row or any column. So what's not a great idea is going across this row, because it would be a lot of work. If I went, say, across this row, that would be better because this has a bunch of zeros. So if I'm doing 0 times this determinant, I don't have to really do the determinant because it's times 0. So we choose a row or a column with a bunch of zeros, and here we actually have both because this is a column with a lot of zeros. So I'll just pick something to do. Maybe I'll choose the row. So one thing we have to be careful about this is the plus minus pattern. Oops. This pen not working. Okay. What I remember is that there's a checkerboard pattern. If you're going across the top row, it's just plus minus. But if you choose a different row or a different column, the checkerboard pattern tells you what to do. So right. So according to the checkerboard pattern, this would be a plus, this would be a minus, and this would be a plus. So going across this row, it's going to be plus minus. So I go 0 times whatever the determinant is if I cover up this row and this column. So, okay, this is silly, but I'm going to write it just so you understand what it would be. And hopefully I don't make a dumb mistake, because that would be a real failure to illustrate what I'm trying to illustrate. But right, it's just the determinant that I would get by covering up the row and the column with this 0 in it. And like I said, it is silly because it doesn't matter at all what this is. That's the point of me using this 0. So I'll go faster as I proceed. So remembering the plus minus pattern, the next one would be a minus, and then it's a 2. And then this determinant actually does matter. So this would be 1, -1, 1. 3, 0, 2, -2, 0, 1. And then I keep going, but let me just scribble for the things that don't matter, right? All right. So we're down to a 3x3 determinant, and we have to actually do it. So these things don't contribute anything. These are dead. So let me do this 3x3 determinant. Of course, I could just use the shortcut for 3x3s now that I'm down to a 3x3. However, since I'm trying to illustrate this, let me expand on this column. Okay, so how does this work? I look at my checkerboard pattern. So the checkerboard pattern has a minus in this position. So I'm going to go minus 1, because this is already a -1, and the other minus is from the checkerboard pattern, times, now I'm down to a 2x2 determinant, so hopefully I'm not doing too much at once, but I would just be down to this determinant, 3, 2, -2, 1. Let me just use the shortcut because 2x2 is so small. So this would be 3 times 1 minus -2 times 2, right? So I'm going down this column. I already did my first one, and then the rest is going to be zeros. So, I mean, I don't really even need to write this. I'm just showing that I thought about it. But right, it's 0 times whatever determinant doesn't matter, and then this 0 times whatever determinant also doesn't matter. So now I've just got to watch me make a mistake in the last part. So this is a 1, this is 3 plus 4, so looks like I get -14. Okay. So we're learning some tricks to do determinants fast. Here, let me show you the last page again. But of course, the last one was sort of concocted to illustrate that. Like when I came up with this example, of course I gave us one with that it has a row that's all zeros except for one thing, and then another column that's all zeros except for one thing. It was definitely chosen deliberately to illustrate how easy it can be when you have that. But that's kind of a coincidence when you have that. So we need to learn how to be sort of more sophisticated. So let's build up to that. So a matrix is upper triangular if all of the entries underneath the diagonal are zero. Like this one. The diagonal, when I say the diagonal, I mean top left to bottom right, and all the entries beneath it are zero. We call it upper triangular because the upper triangle is considered like this top triangle, and that's where all of the non-zero entries are. By the way, we would say this is lower triangular if it was kind of the other way around. If all the non-zero entries were on the lower triangle, and then up here we would have zeros, we would call this matrix lower triangular. And here is a fact that I'm going to illustrate. I'm just going to illustrate it by an example. But the determinant of a triangular matrix, whether it's upper triangular or lower triangular, doesn't matter. The determinant is the product of its diagonal entries. So if you trust me completely, we know the answer to this. This should be 1 times 4 times 6. That's the product of the diagonal entries. I'm going to actually sort of show some work. I mean, you know, it's feel free to use this shortcut in the future whenever you like, but I'm not just going to use the shortcut because I want you to sort of, I want to illustrate why it's true. Well, I can expand on, say, this column. My checkerboard pattern would put a plus here. And then I would get this determinant. And of course, 0 times something I don't care about, and 0 times something I don't care about, right? And then, just to be silly, even though I'm already down to a 2 by 2, let me expand on this column. Well, according to the checkerboard pattern, this would be the top left, so this would be a plus. And of course, you know, I'm supposed to multiply by this determinant, which is just, this is a 1 by 1 determinant, which is just the number inside. So I get 1 times 4 times 6, the product of the diagonal entries. So hopefully that sort of illustrates why you get that. Anyway, sure enough, we get what we're supposed to get. Okay, but how does that help, right? I'm trying to show you shortcuts to find determinants, and with the last shortcut, I sort of complained that it only works if you happen to have a lot of zeros in the right places, and that's also true in this case. It's kind of a coincidence if you happen to have an upper triangular or lower triangular matrix. It requires you to have a bunch of zeros in specific places, and it's a coincidence if you do. So, how do we use that? Here's how we use it. We have been learning how to do row operations on matrices. And what I can tell you is a couple of rules for if I start with one matrix whose determinant I want to know, and then I do some row operations to that matrix, how does the determinant of the original matrix relate to the determinant of the new matrix? And I'm not going to prove any of these things. I'll just tell you what's true. If I obtain the matrix B from the matrix A by swapping two rows, then the determinant of B is just going to be the opposite sign of the determinant of A. If I take A and I multiply a row by some non-zero scalar, C, then the determinant of B is 1 over C times the determinant of A. And the last one, this is something we often do. We often add a multiple of row J to row I, and then we write the result where the old row I was. In other words, we replace row I with row I plus C times row J. Then that actually has no effect whatsoever on the determinant. The resulting matrix B has the exact same determinant. One thing that is important here, we're replacing row I with this, and row I is not getting multiplied by anything here. We're not replacing row J with this. So that's important, but that will usually be the case. If we wanted to replace row J, then basically, the quick version is we would have to use this second fact. There's still a way to figure it out, but yeah. Okay, let's do a 4x4 determinant that doesn't have any obvious way to do it quickly. So just to talk about some ideas that we don't really want to go with, I could use the definition. I could go across the first row, but I'm going to have a 3x3 determinant for this, another 3x3, another 3x3, and another 3x3. I could try to be smarter and look for a row or a column with a lot of zeros, but actually there's no zeros at all. So that, there's nothing I can do. And this is not upper triangular or lower triangular or anything like that. I have no zeros anywhere. So what do? I'm going to do some of this stuff. I would like to get this to be a triangular matrix, and we have the tools to do that. We have row operations, and getting it to be an upper triangular matrix is basically what we've been doing when we get matrices in echelon form, or that's how we're going to approach this, is by getting this in echelon form and just hoping that it's upper triangular, we could say. All right, so what do? I would like a 1 here, and I've got it. I want zeros underneath that 1. Here, let me do this thing where I sweep from left to right. I like that. I'm going to use my 1 to get my zeros. And by the way, let's not be too scared, because I'm about to do several operations at once. I'm just using this third type of operation. I'm replacing row 2 with row 2 plus a multiple of row 1. And that operation has no effect on the determinant. So let me do several of this type of operation at once, and with the confidence that this has no effect on the determinant. So I can simultaneously do row 3 minus 3 row 1, row 4 plus row 1. Zero, 6 minus 4, negative 1 minus 2, 3 minus 4, okay, 3 minus 3, of course this better be a 0 if I remember what we're doing, 6 minus 3 times 2, 5 minus 3, 10 minus 6. Okay, and then this one better be a 0 if I remember what we're doing. This plus this. 1 plus 1. 3 plus 2. Okay. So where are we now? I'm happy with this column. Let's move on to the next column. And for this, I don't really need it to be in reduced echelon form. If I did, I would want a 1 here, and I would also want zeros above it. But let's remember what I'm doing. I just want this matrix to be upper triangular. I'm okay having non-zero entries up here. An upper triangular matrix is allowed to have non-zero entries on the diagonal and above. Really, I care about the zeros underneath. So actually, also I don't need a 1 here for just echelon form or upper triangular form. So actually, I'm already happy with this column. So let's keep moving. I'm not quite happy with this column. I would like this matrix to be upper triangular. So here's my diagonal, and I want zeros below the diagonal. So this 2, I'm not so happy with this 2. So there's a couple of things I could do here. Maybe I'm probably not going to do the most obvious thing. The most obvious thing would just be to take row 4 minus row 3. Because I want to illustrate more of these rules that we just learned, and so far I've only used the third one. Let me show you, because I don't need this to be a 1, but let's make it a 1 anyway, just to illustrate something. So what I'm about to do is, I'm about to do 1/2 row 3. So in other words, like I'm multiplying a row by a half. So the determinant of the resulting matrix is going to be 1 over a half times what I get. By the way, of course, this is just a 2 in front. The way I actually think of this in my head is it's like I'm pulling a 2 out of this row. And if I view it that way, I pull a 2 out, I get a 2, and this is the same as 2. And then I pulled a 2 out, so everything in here is half of what it was. Anyway, right. I still want this to be a 0. I want zeros all the way underneath the main diagonal, and this is the only non-zero entry left underneath the diagonal. So let me kind of finally kill this. Row 4 minus 2 row 3. So of course this is 2, and then got a bunch of stuff that doesn't change. Zero, 0, this better be a 0, and 5 minus 4 is 1. So I've got my 2 from the outside, and the determinant of a triangular matrix is the product of its diagonal entries. So I go right down the diagonal. And we get it. So, okay, I have one small confession. I did kind of construct this example so that it would be nice. Like, if you noticed, when I got these numbers to be zeros, so in other words, I got these to be zeros, I set it up so that these would automatically be zeros. I mean, I constructed the example so that we would sort of miraculously get more zeros than we bargained for. So this is still a little bit of a concocted example just to illustrate something, but this is in general a fairly, like a reasonably efficient method in practice. If you have to do a 4x4 determinant by hand, this is a reasonable method. Try to get it upper triangular using these row operations. All right. So let me just sort of state a couple of random facts here at the end, just relating determinants to other matrix operations that we've learned about recently. So here's how determinants behave with respect to matrix multiplication. If I take the determinant of A times B, that's the same as just the determinant of A times the determinant of B, and I'm not proving this. Here is a related fact. The determinant of A inverse, assuming that A has an inverse, of course, the determinant of its inverse is, I've written it here in a little bit of a funny way. Of course, the determinant of a matrix is just a real number, and when I take a real number to the -1 power, that's like writing 1 over that. I sort of like it this way because it's sort of like, well, it's sort of like I just took this -1 and moved it on the outside of the determinant signs. But it can also sort of a little bit obscure the meaning. Of course, like I said, when I talk about a real number to the -1, that's the same as 1 over that. And of course, we are not dividing by 0 because if we were dividing by 0, the determinant would be 0, which would mean that the inverse doesn't exist. So there isn't a problem there. And yeah, by the way, since I sort of have a minute here, I'm not proving many things, but let me prove the second one, and I'm going to assume that the first one is true. What should happen if I take the determinant of A times A inverse? Well, on the one hand, we're assuming that the first property is true. If you'll allow me to assume that. So that should give me the determinant of this times the determinant of this. On the other hand, I know what A times A inverse is. It's supposed to be I. And if we think about the determinant of I is actually upper triangular because it has zeros underneath the diagonal. By the way, we could also say it's lower triangular because it has zeros above the diagonal. So either way you want to look at it, the determinant of I is the product of its diagonal entries, and the diagonal entries are just 1, so we're just going to be doing 1 times 1 times 1. So the determinant of the identity matrix is just 1. So now I can solve for this. Like I'm trying to justify this property so I can solve for the determinant of A inverse, and I'll get there. So I'm just going to do 1 divided by this and get the answer I expected. Okay, great. So I proved one thing. I didn't prove a lot of other things, but I'm okay with that. So let me talk a little bit about this other fact, because from Calc 3 you might remember determinants a bit, and I'm going to try to draw a connection for that. So if we have a linear transformation, so it's a function from Rn to Rn, like n-dimensional space to n-dimensional space. And you may remember from Calc 3 that a linear transformation from Rn to Rn is going to be given by like a matrix formula. So there's some matrix A such that the way I evaluate f of some vector x is I always just do this matrix A times x. And the general fact that you may remember, you may be more familiar with this in 2 dimensions or 3 dimensions, but I'm sort of going to n dimensions in general. This linear transformation, so to speak, it blows up the hypervolume by a factor of absolute value of the determinant. And right, these really are absolute value signs. These are like, I know that it's a little bit confusing because sometimes we use vertical lines to denote the determinant of A. Here I literally mean you take the determinant, and if it's negative, then you switch it to positive. So these are absolute value signs. So the relevant fact you might remember, or one of them from Calc 3 that you might remember, is like the image of the unit cube. If you're in 3 dimensions, the image of a unit cube is this shape that we call a parallelepiped, and you can find the volume of that parallelepiped by doing a determinant. In general, if you take the image of the unit hypercube, so that's like a 1 by 1 by 1 by however many ones you need because we're in n-dimensional space, that's the unit hypercube, and you look at the image of that under this linear transformation, the image in general, so in 3 dimensions we call it a parallelepiped, in 2 dimensions we call it a parallelogram, in arbitrary numbers of dimensions we call it a parallelotope. And its hypervolume, which is just like the natural generalization of volume to n dimensions, is given by the absolute value of the determinant again. This is also relevant, if you remember, to the Jacobian. To when you do a substitution for a multiple integral, you have to multiply by this thing we call the Jacobian, which is a determinant. And it is essentially measuring how much this transformation blows up the volume or shrinks the volume. And it's essentially for this exact reason that when we make a substitution for multiple integrals that we have to use the Jacobian. It's the fact that the volume is getting blown up or shrunk.